Draw a line on a map, 170 kilometers. Perfectly straight, from the Red Sea coast, through rocky desert, into the mountains of Tabak. Simple, right? On paper, the line was exactly that. A line, a single, unwavering stroke across the Saudi Arabian landscape. The promotional videos showed it as a perfect geometric form, two mirrored walls, stretching to the horizon without deviation, without compromise, without bending to the land beneath. But the Earth doesn't care about geometry, and the Earth beneath a line is not one landscape. It is dozens, perhaps hundreds, each with its own rules, its own chemistry, its own way of destroying the foundations you try to build. When Crown Prince Mohammed bin Salman announced the line in January 2021, the route had already been chosen, not by geologists, not by engineers, by vision. The line would be straight because straight was dramatic. Straight was iconic. Straight would look spectacular in drone footage. No one asked what the ground would think. This is the story of what happens when you try to build the world's largest structure across terrain that changes every few kilometers. When coastal sand meets volcanic rock, meets ancient riverbeds, meets mountain granite, when the soil that holds your foundation in one location dissolves your foundation in another. 170 kilometers. Each one a different problem, and no one solution that works for all of them. Let's begin where the line was supposed to begin, the Red Sea. The first kilometers would rise from the coast itself. Promotional images showed the mirrored structure emerging dramatically from the water's edge, reflecting both sky and sea. It was meant to be breathtaking. It was also meant to be built on some of the most unstable ground on the planet. Coastal zones along the Red Sea are characterized by sabco, a geological term for salt flats, created by tidal flooding and evaporation. Sabkha soil is saturated with salt. It expands and contracts with moisture changes. It has almost no load-bearing capacity. Try to build a foundation on sabkha, and it doesn't just sink. It shifts. It heaves. It cracks. The salt corrodes any steel it touches. The moisture penetrates any concrete you pour. Standard construction on sabkha requires either removing the entire layer sometimes, meters deep, or driving piles through it to reach stable ground below. For a small building, this is expensive, but manageable. For a 500-meter wall stretching kilometers along the coast, it's a nightmare of biblical proportions. But sabkha was just the beginning. The coastal zone also sits in a seismically active region. The Red Sea is a rift zone, a place where tectonic plates are slowly pulling apart. Earthquakes are not common, but they occur. And when you're building a 500-meter tall continuous structure, even moderate seismic activity poses catastrophic risks. Engineers working on the line discovered that the coastal sections would require foundation systems unlike anything previously constructed. The piles would need to be massive. Some estimates suggested 3 meters in diameter. They would need to penetrate through unstable sabkha, through intermediate layers, down to bedrock that in some locations lay 20 or 30 meters below the surface. And every single pile would face corrosion from the salt-laden environment. The sea that was supposed to make the line beautiful was actively trying to destroy it. Move inland from the coast, and the geology changes. Sabkha gives way to sand. Endless, shifting, ancient sand. This should have been easier. Sand is familiar. Humans have been building on sand for millennia. The entire city of Dubai rises from sand. But the line wasn't building a city, it was building a wall. A continuous, rigid, 500-meter wall that needed to remain perfectly aligned across dozens of kilometers. Sand moves. Not dramatically, not quickly, but constantly. Wind shifts the surface. Subsurface water levels fluctuate with seasons. The weight of structures causes gradual settlements, sometimes uniformly, sometimes not. For conventional buildings, differential settlement is managed through expansion, joints, and flexible connections. Buildings can shift slightly relative to each other without catastrophic failure. This is standard engineering. The line had no such flexibility. The design called for 2 continuous parallel walls. Any differential settlement at any point where one section sinks differently than the section beside it would create structural stress. Cracks, failures, catastrophe. To prevent this, the foundation system would need to ensure absolutely uniform load distribution across the entire length. Every pile would need to reach the same bearing capacity. Every section would need to settle at exactly the same rate. In uniform soil, this is difficult. In sand, that varies in density, composition, and water content from location to location. It's nearly impossible. Geotechnical surveys revealed the truth. The sand along the line's route was not uniform. Some sections were densely packed, capable of bearing significant loads. Others were loose, prone to liquefaction under stress. Still others contained clay lenses, thin layers of clay within the sand that behaved completely differently under load. Each variation required a different engineering solution. But the line's design didn't allow for variations. The wall had to be continuous. The foundation had to be consistent. The geometry was non-negotiable. The sand didn't care about geometry either. 40 kilometers inland, the geology transforms again. Here, the line's route crossed Herat volcanic fields created by ancient lava flows. The Arabian Peninsula sits on a tectonic plate that has experienced volcanic activity for millions of years. The evidence is written in the rock. Herat terrain is characterized by basalt hardite, volcanic rock that forms when lava cools. Building on basalt sounds ideal. It's strong. It's stable. It doesn't shift or settle like sand. But basalt comes with its own problems. First, it's incredibly hard. Drilling through basalt requires specialized equipment and enormous amounts of time. The same pile that could be driven into sand in hours might take days to drill into basalt. Multiply this by thousands of piles, and the timeline explodes. Second, basalt is often fractured. Lava doesn't cool uniformly. It cracks as it solidifies, creating networks of fissures throughout the rock. These fractures make the rock's behavior unpredictable. What appears solid on the surface might be riddled with voids below. Third, the transition zones are the most dangerous of all. Where sand meets basalt, you get the worst of both worlds. Foundations that start in one material and end in another experience differential stress. The rigid basalt doesn't move. The sand beside it does. The interface becomes a failure point. The line's route didn't just cross volcanic fields. It crossed the edges of volcanic fields multiple times. Each transition zone represented a unique engineering challenge with no standardized solution. Engineers began to realize that the straight line on the map actually crossed through geological complexity that would normally be avoided entirely. Routes for pipelines, highways, and railways are carefully planned to minimize geological transitions. The line had been planned for visual impact, not geological feasibility. The rocks beneath the desert were teaching a lesson that no promotional video had anticipated. Between the coast and the mountains, the line's route crossed something invisible but deadly. Wadi is the Arabic term for a valley or channel created by water flow. In the desert, wadis are dry most of the year, sometimes dry for years at a time. They look like ordinary desert terrain, but wadis, remember water. The soil beneath a wadi is fundamentally different from the soil beside it. Centuries of periodic flooding have deposited layers of silt, clay, and gravel in complex patterns. The water table is often higher beneath wadis, even when the surface is bone dry. The ground can be saturated just meters below a dusty surface. When it rains in the Saudi Arabian highlands, and it does rain, sometimes torrentially water rushes down these ancient channels with devastating force. Flash floods in wadis kill people every year. They destroy roads, bridges, and buildings. The line's route crossed multiple major wadis. The design called for the structure to simply pass over them, supported by foundations on either side. But the foundations on either side would be built in wadi ashen soil, soil that behaves differently than normal desert ground. Worse, the wadi crossings created hydraulic challenges. When flash floods occur, water needs somewhere to go. Block a wadi with a 500-meter wall, and you create a dam. Water builds up. Pressure increases. Either the water finds a way around potentially undermining foundations, or it finds a way through. Drainage systems could theoretically address this, but the scale was unprecedented. The line would need to pass millions of cubic meters of potential floodwater through or under the structure during extreme weather events. The engineering for this alone represented a massive undertaking. And each wadi was different. Different depth, different soil composition, different flood patterns, different solutions required. The desert looked empty and uniform from above. Beneath the surface, it was a maze of ancient waterways, each one a trap for the unwary builder. The final third of the line was supposed to climb into the mountains of Tabak province. Here, the promotional videos showed the mirrored walls rising against dramatic cliff faces, reflecting peaks and valleys in their glass surfaces. The geology of mountains is the most challenging of all. Mountains are made of rock, but not uniform rock. The Tabak Islands consist of sedimentary layers folded and faulted over millions of years, interspersed with igneous intrusions and metamorphic zones. The rock type can change completely within a few hundred meters. Sandstone, limestone, granite, shale. Each behaves differently. Underload. Each requires different foundation techniques. Each weathers differently, erodes differently, fractures differently. Mountains also have slopes. The line was designed as a vertical structure on horizontal ground, but the mountains aren't horizontal. Building a 500-meter vertical wall on a slope requires either massive earthworks to create level foundations, or complex foundation systems that can accommodate varying elevations. Neither option had been adequately addressed in early planning. Then there's the issue of rock stability. Mountains look permanent, but they're constantly changing. Rockfalls, landslides, and slope failures occur naturally. Add the vibration of construction, the weight of massive structures, and the alteration of drainage patterns, and you accelerate these processes dramatically. Geologists, reviewing the line's mountain route, identified multiple areas of concern zones, where the rock was fractured, where slopes were marginally stable, where construction itself might trigger failures. These weren't hypothetical risks. They were documented geological realities. The mountains that were supposed to provide the line's dramatic backdrop were actively hostile to its construction. By 2022, geotechnical surveys had revealed the full scope of the problem. The line's route crossed at least 7 distinct geological zones, each requiring fundamentally different foundation approaches. Coastal sabuka, sandy desert, volcanic basalt, wadi crossings, sedimentary foothills, metamorphic transition zones. Mountain bedrock. There was no single foundation system that would work everywhere. The engineering teams faced an impossible choice. They could design multiple foundation systems, one for each geological zone, and somehow connect them seamlessly. Or they could over-engineer everything to handle the worst conditions at astronomical cost. They chose the second option. The piles driven into the desert became some of the largest ever constructed, 2.5 to 3 meters in diameter, drilled tens of meters deep, regardless of whether the conditions required it, reinforced to handle corrosion, seismic loads, and differential settlements simultaneously. A construction specialist who worked on the line told the Financial Times, "Some of these piles are the biggest in the world. They're absolutely colossal." 60 piling rigs worked around the clock, installing 60 to 65 piles per day. Approximately 6,000 piles were drilled into the first 2 kilometers of desert. The foundation work alone cost several $1 billion, and it was only the beginning. The foundations for the remaining 168 kilometers would face even more varied conditions. The geological surveys kept revealing new challenges. Each solution created new problems. One engineer described it simply: "We were fighting the Earth itself, and the Earth doesn't lose." A reasonable question emerges from this geological nightmare. Why didn't Saudi Arabia know about these challenges before announcing the line? The answer reveals something important about how megaprojects fail. Proper geological assessment for a project of the line scale would require years. Thousands of boreholes along the entire route. Detailed mapping of every geological transition. Laboratory analysis of soil and rock samples. Seismic surveys. Groundwater studies. This work should happen before a project is announced, before a route is finalized, before a design is locked. For the line, it happened after. The route was chosen for visual and symbolic reasons, a straight line from sea to mountain, demonstrating Saudi Arabia's bold vision. The announcement was made. The promotional videos were released. The world was told that construction would begin immediately and completion would come by 2030. Only then did the detailed geological surveys begin. What they found was devastating. The route that looked so perfect on satellite imagery was a geological obstacle course. The straight line that seemed so simple crossed every possible type of challenging terrain. But by then, changing the route was politically impossible. The Crown Prince had announced the vision. The world had seen the renders. The line had to be straight, had to run from coast to mountains, had to be exactly as described. Engineering would simply have to solve the problems. Money would overcome geology. This is the fundamental error of authoritarian decisions are made for symbolic reasons, then reality is expected to comply. When reality refuses, the options are limited. Admit failure publicly, or spend unlimited resources trying to force compliance. Saudi Arabia chose to spend the resources, billions of dollars in foundations designed to overcome geological challenges that proper planning would have avoided entirely. And still, the Earth refused to cooperate. By September 2025, when construction was suspended, the geological challenges remained largely unsolved. 6,000 piles stood in the desert monuments to the first 2 kilometers of a 170-kilometer route. 2 kilometers of the most straightforward terrain. The really difficult geology lay ahead. The volcanic fields hadn't been crossed. The major wadi systems hadn't been bridged. The mountain zones hadn't been touched. The transitions that engineers feared most remained in the future, a future that might never arrive. What does this tell us? Perhaps it tells us that some projects are too big for the Earth they're built on. That geological complexity cannot be overcome simply by spending more money. That the ground beneath our feet has rules older than any human ambition. The line tried to impose geometry on geology. A straight line across, curved, folded, fractured, flowing earth. A rigid structure on ground that shifts, settles, heaves, and erodes. A permanent monument on a planet that is permanently changing. Every civilization learns this lesson eventually. The Romans built straight roads, but they routed them around mountains. The Chinese built a great wall, but it followed the terrain rather than defying it. Modern engineers route pipelines, railways, and highways along paths of least geological resistance. The line rejected this wisdom. The line would be straight because straight was the vision. The Earth would simply have to accommodate. The Earth declined. Today, the foundation piles stand in the desert like gravestones. Each one represents a battle fought against the ground, a battle won at enormous cost in that specific location. But the war stretched 170 kilometers across terrain that grows more challenging with every step inland. The sabkha still corrodes. The sand still shifts. The volcanic rock still fractures. The wadis still flood. The mountains still crumble. And somewhere in the vast geological archive of the Arabian Peninsula, the record is being written. Here, in the early 21st century, humans tried to draw a straight line. The Earth said no. 170 kilometers of chaos, each kilometer a different problem, and no solution that works for all of them. The line was supposed to be straight, but the Earth has no straight lines. Only curves, folds, fractures, and the patient, grinding work of time. Perhaps that's the final lesson of the line. Not that the vision was too bold, but that it was too simple. The world is not a blank canvas waiting for geometry. It is a complex system with its own rules, its own history, its own way of humbling those who refuse to learn. The line drew itself on the map. The Earth erased it.